today I'm going to try to give you, in like my normal sort of ad hoc way, my understanding of what target decoy searches are, like data dependent analysis, like and talk about how we use them, and to talk about ways where they work well and kind of ways where they fall short. And so go ahead and like fire away questions, as you have them. But the first thing I just kind of wanted to pop up here for those of you guys that are sort of interested in going back and like looking at historical papers in this area. This is the paper where the strategy was like really introduced and first shown to be like a viable strategy for providing confidence metrics to large scale data dependent analysis proteomics experiments. And so you guys can track that down and have a read. Okay, so before I kind of get into it, I want to go back just a step and talk about like what data dependent analysis is. Okay, and then it'll be making more sense like why we're using this sort of target decoy strategy. So data dependent analysis has been like the most common way to do large scale proteomics for like the last several years. Recently, there's something called data independent analysis, which is like become sort of equally competitive with DDA, but that's been in the last few years, and that's like not something that we've been doing in our laboratory yet, although I think we'd like to, because there's lots of benefits to that. So what data dependent analysis means is that the data is sort of dictating like what peptides get fragmented and then ultimately capable of being identified with a database search. So we have an experiment where peptides or proteins have been digested into peptides. They're put into a capillary column, and as they pass through the column in solvent, they stick at different rates depending on their hydrophobicity and other things, and there's a separation that occurs. And out of the other end of this capillary, sort of peptides with the same properties kind of elute at the same time. And the first thing that's done is we take a snapshot of all their intact masses. This is called like an MS1 spectrum. And so at any given time, there can be like many dozens of peptides co-eluting at different abundances. And so we just take a picture of that, okay? And then most generally, we set the instrument up to just have a look at those things, and maybe they'll pick the top 10 or 20 peaks to isolate and then to fragment further, okay? That's called an MS2 spectrum. So where one peak is isolated and then there's fragmentation. There are like rules for the selection. The computer can remember that you've picked a certain mass and like not pick it again, or not pick it again for like a few minutes, or pick it only 3 times. That's like quite common. But it's safe to say that not all things get picked. And if you were to kind of do replicates, not all the same things would be picked in replicates, okay? So once we have the experimental spectrum, we try to match it up to a set of theoretical target and decoy peptides, okay? So we're sort of like getting into the target decoy experiment. But basically, peptides like subjected to fragmentation break along the peptide backbone, sort of between amino acids. And so, and typically peptides only break once. And so you get part of the peptide, there's like they call it a B side, and the other part is called the Y side. And basically you get a ladder that runs. And so if you have a database of proteins and peptides that you sort of believe to be in your sample, we can kind of match it up with that. All right. As far as scoring the match, there's lots of different scoring algorithms that exist. Okay. But our particular algorithm, the algorithm we use in MetaMorpheus, it's basically just a count of matching peaks, which is an integer. And then we also tack on the fraction of matched intensity. Okay, so just sort of like normalize to 1. So if you normalize all the intensity of spectra to 1, and then you match like half of those peaks, then basically you'd have a fractional intensity of like 50%. Okay, we assume, like the assumption here is that that the protein sequence list, the proteome, the database that we're using, accurately represents what's in the sample. Okay, we've talked about limitations of that, and we're reporting like the best match between target and decoy. So it's a winner take all thing. We're not reporting the best target match or, you know, that's not a separate list. Every experimental spectrum basically gets kind of like matched to like one thing. And, you know, if the best match happens to be a decoy, then that's what we assign it. Okay. You know, as I mentioned, like there's like some concerns with this approach.
Do you think you could go over like what an E value is?
Yeah, I got it listed down below when we talk about the individual metrics. I will get there, Gloria. With the data dependent approach, as I said, the selection of candidates is like stochastic. And so if you see or don't see something, it isn't necessarily like a guarantee of its existence or non-existence. Okay. So typically, and this is just one of those like back of the envelope numbers that I use. If you ran 2 technical replicates of the same sample, you just injected it twice, you get about 66% overlap in peptide identifications, just so you get kind of a feel for the level of stochasticity, if that's even a word, okay? The other thing is almost like never do we get complete coverage of a peptide sequence, okay? Almost, I mean, I literally can say every peptide match that we get is based on partial information, okay? And I'm going to give you some examples of like annotated spectra. But what that means is that, you know, we really need like a statistical belief about that identity based on the composition of the databases we use. There, you know, like it's just like, unless we did some heroic experiment, you know, there's always going to be some loss in confidence about like whether a particular assignment is correct. And then kind of like the last thing is that it's like there's some levels of ambiguity that are really tricky, okay? Leucine and isoleucine have exactly the same mass. We can't differentiate them, like basically can't differentiate them within the mass spectrometer. And so peptides that differ by I and L, and there are examples, not surprisingly, can't be resolved. If there's a PTM on the peptide, and that's like not uncommon, if we don't have coverage in the fragmentation of that PTM, then we can't necessarily localize it. So there can be ambiguity of the peptide. If you don't see that PTM, like in the places where we don't have fragments, it can like move around if there's like multiple spots for it. And then also it's not uncommon, especially for like smaller peptides, to have amino acid transpositions. So a peptide might be like PEPTIDE, or it might be PETPIDE, you know, where P and T got transposed. And so the mass of the thing is exactly the same. The amino acids are exactly the same. But if we don't have fragmentation coverage, can't resolve those transpositions. And I'll show you some like real examples of these things in just a second here. Okay. So let's talk about the Decoy database for just a second, okay? And I'm going to show like some. I know this is like a lot of text, but I'll be showing some results here pretty soon to like put some like numbers and examples on these words. A decoy database used in these types of experiments, we really need the size of the decoy database to match exactly, like more or less, the size of the target database. You can imagine like when you're trying to match spectra to either one, if the size of the database didn't match exactly, you'd have some bias immediately. You know, if the decoy database was 5 times as big, you know, you just have like 5 times more chances of like matching to the decoy database. And so we really try to get those to match up. Something that's like not totally obvious, okay, is that when you're matching against decoy peptides, they really have to look like real peptides, okay? Mother Nature arranges her amino acids in a certain kind of like an order and distribution, right? And so if you were to make a decoy database simply by random choice, you just got 20 amino acids and you're going to plop them together in like random order, it doesn't make for a very good decoy database because amino acids just aren't arranged like that in nature. Okay, you can sort of like under bias against it. And so typically what we do is like sort of reverse these things. And so like on a protein level, the composition of amino acids within that protein will be preserved. And then the distance between certain amino acids will be preserved, like lysines and arginines, which is the things we cut at. Okay, so sort of continuing that thought, we really need to keep we need to preserve the amino acid abundances for the target and decoy database. Like you can't move those around. As I said before, just randomly picking the 20 amino acids would be bad unless you already sort of predetermined the fraction of each one within the target database. Like you could sort of, you could do it that way. This next thing is like absolutely like a key. And if you go back to that Josh Elias paper, when we're talking about false positive matches, these are like low scoring things. A spectrum which matches to a false positive target or a decoy, the probability should be like exactly equal. There shouldn't be any bias there at all. And I'm going to show you data on that from a real experiment that I did in preparation for this talk. And you'll sort of see what I mean by that. And then the last thing is that there should be no overlap. You can imagine, if you have a large target database, if you simply reverse it, which is the most common thing that we do, that you can end up with decoy peptides, which are present in the target database. And so we have to like eliminate or switch those, okay? So that, we don't have any sort of like mix-ups there. So the data I'm about to show you comes from this paper by Matthias Mann. I use it all the time. This is, he did this experiment where they took 11 really common cell lines and they simply digested it, fractionated, and ran it multiple times. And so it's just like super handy. I keep it around all the time. And the particular data I'm going to show you is from their HeLa sample, okay? And so I ran this HeLa sample through MetaMorpheus. So this is like this is a pretty typical experiment. For this one sample of cell lysate, I got 158,000 PSMs, 52,000 peptides, and 6,000 proteins. Like there's a lot of experiments now with like, sort of like newer mass specs that are pushing the number of proteins beyond 6,000, 8,000, 9,000, 10,000. Is like not unusual, but like hard to do. And there's like extra statistical problems that arise when you get that deep. But this is a pretty common experiment. I also kind of wanted to show you the Ptm variety that I see in this kind of data. The first one you see on this list, carbamidomethylon C, that is a sample processing thing. And so we reduce and alkylate all the cysteines to kind of open up this, so proteins cross-link at cysteine residues. And so to enhance the digestion, we reduce and alkylate that. So that's a thing we add. Oxidation of methionine happens like both naturally and also as an artifact of sample processing. It's always like quite high. Deamidation typically it's sort of the same story there, where some are real, but many are introduced through sample handling. And then we see the first incidence of like real sort of biological PTMs. Acetylation is super common. Phosphorylation of serine is like really common. I think that's really just all I wanted to kind of note here, but just sort of seeing like the variety of things that we sort of see. So here's the first data slide I want you to clue in on, and this is maybe like the most important slide in like the whole talk. And so if you got questions, this would be a good place to fire them at me. So what I did was the PSMs that were identified in that last experiment are sorted by score. Okay, so the top scoring PSM is at the top, and then it goes all the way down to the lowest scoring PSM. Okay, and then what I have here is a histogram of those things by score. So the score is along the x-axis here. So 40 something was the highest scoring PSM, and 2 are the lowest scoring PSMs, okay? This orange curve, which is obscured by this gray curve here and continues on out, that is a histogram of targets, okay? The blue curve is a histogram of decoys, okay? So you can see automatically that at high score, we only see targets, okay? And then up to this point here where we have this yellow line, and then there's a break, and then it goes up, okay? And the reason that the orange curve is higher than the blue curve here is because if you see, I sort of like I subtract like orange minus like blue, which gives the apparent actual distribution of targets. It's just the summation of like false positives and like true negatives. All right, that's why it kind of goes up. Incidentally, what this yellow line is, the 1% cutoff. And so, can I move this over here? Yeah. And that's our 1% FDR cutoff. All right. And what that means is that of the area of this sort of gray area, okay, 1% of the area is covered by this blue area. Okay. So 1% of this volume, okay, above the yellow line, those things are false positives. Okay. And how we compute that is just a ratio. So we count the decoys. So that'd be like a sum of all these blue things, and then divided by the targets, which is the sum of all the orange things, okay? And so that's at 0.01. And so one thing I kind of want to point out is that if you look at the gray bin here below the yellow line, there's like 31,574 PSMs below that. And so those are like real identifications that are being like lost to this cutoff, okay? Furthermore, that this FDR cutoff basically applies to every target above this. And what that means is that any PSM that has a score above 7 point whatever this is, has a 1% probability of being a false positive, okay? We don't know anything about which ones those are. It simply applies to the entire group. There's no peptide level error that comes here, okay? I'm gonna talk about how we get to computing statistics for individual peptide identifications in a second, but do you guys have any questions about this graph and how we construct it and how it's used?
Yeah, a good one. So what if you were to do the same based on intensities? Can you, so first question, can you compute the intensity of the decoys? And if you can, do you think it would allow you to have such a clear distinction that you also have here?
Right, that's a good question. I'm gonna show you some data when I get into talking about how we derive individual confidence metrics, where we take into account the intensity, okay? We don't do it at the group level, all right? But we can and do it at the individual assignment level, okay?
Okay, thanks.
Anybody else? All right.
I guess I have one question, just more about with the fields. You know, in the early days, people were using FDRs of 5%, 10%, and now it seems like we're using 1%. And can you just make a brief comment on, is that pretty much what people are doing, or does it really, it depends, right, on the experimental goals, what our cutoff is?
Right, I think so. Like, I mean, I have no idea why we pick these numbers, like, because I guess they're round numbers, like why not 2% or 0.5% or like whatever. I guess we just like whole numbers. And I guess I'm just gonna make up an answer, is that quite typically in these kinds of experiments, if we choose a 1% cutoff, we have like lots of fun things to kind of look at. We're not feeling too compromised. I will tell you though, that in top-down experiments, and I'm not really talking about top-down experiments here, okay? The number of different things we identify in a DDA type top-down experiment of complex samples is really low. We got a lot of PSMs for exactly the same thing over and over and over again. There's very little variety. It's only the most abundant proteins and the lowest molecular weight. And so typically, you know, all of the interesting stuff is like missing, right? It's too low intensity, it's too big for a mass spectrometer. And so there, it's not unusual to kind of go to 5%. And that's like simply like a grab. Does that make sense? So like we didn't see anything interesting in the 1% list. And so we go to like 5% just in the sort of like vain hope that some more interesting proteoforms will show up.
Yeah.
But I think it's like not such a problem for bottom up.
And then I was also thinking that it depends on what we're doing with the data downstream. So if these identifications are going to be validated, then you could maybe even accept a very high false discovery rate because you're going to validate it eventually.
Sure, absolutely. Yeah. And we haven't really talked about, like I said, there are individual confidence metrics. And so, then you can sort of stop thinking about this group-wise confidence metric and think about the individual peptide confidence metric if you want to switch around, okay? Which basically goes towards your point about individual validation, right? If we're going to look at individual peptide assignments based on like whether they're real or not, then that's like a different set of peptides.
Mhm.
All right, so I'm just going to show two
Oh,
annotated.
I'm sorry. I actually have one last question about units. So the unit here is the spectrum. So the peptide spectral match. Can you maybe you'll talk about how we aggregate to the peptide level?
Right. All right. So the only difference, so one is we do exactly the same kind of graph at the peptide level. There's no difference. But what we do is we take the top scoring PSM for each peptide sequence. Okay. So for one peptide sequence, you might see 5 or 10 or 15 or 20 different spectral matches. We simply pick the top scoring one to put in the table, okay? So we construct a smaller table, again, of target and decoy matches. And in this case, it's just the best scoring PSM for each one and sort it from top to bottom. Otherwise, graphically, there's no difference, and computationally, there's no difference. It's just a subset of the best matching PSMs.
Okay. So what do you recommend? To just go with either approach or?
Oh, so I've been just like wondering this like in my head lately if PSMs have any value at all. We in our lab basically never use PSMs as a quantitative like measure of abundance. I think it can kind of work okay for like medium and higher level abundance sorts of things, but at like low level, PSMs are like a really like noisy count. Not to mention the fact that like one of our students wrote like an excellent program for intensity-based quantification. So, given the stochasticity, we can kind of go back and look for peaks that weren't necessarily selected, but we've seen in other spectra. And so we could get pretty decent measures of peptide quantity by looking at the MS1 intensity or the MS1 integrated peak areas. That's like something that's like in our wheelhouse to do. And I feel like that's the sort of at the current time, that's the best quantitative measure we have of a peptide abundance. So I don't really ever pay that much attention to lists of PSMs. I don't find them very interesting or useful, but rather I'm like more interested in the peptide lists because that's just sort of like the reduced list of unique peptides. And that's when we're doing protein inference, which is a thing we're often interested in doing, PSMs don't factor into protein inference, okay? Only the peptides factor into protein inference, so they're not all that useful. Within a peptide list, we often have a column that says like how many PSMs we saw of a particular peptide. But again, I feel like it's, in the early days of DDA, it was really common to use PSM counts as a measure of abundance. And as the field evolved towards intensity-based measurements, there's still some practitioners of that, but I think for the most part that's kind of gone away. So is that answering your question?
Yeah.
I do just want to make a clarifying statement. We do use PSMs for protein inference. The PSMs are our input for the protein inference algorithm, but they are quickly collapsed just to like a sequence basis. But like we do take the 1% PSMs as our input for protein inference, not 1% peptides.
Oh, okay, thanks, Rachel.
Sorry, again, you said the two best measures of abundance are MS1 intensity, and I lost the second one, MS2 something.
Oh, no, so let me clarify. So I did talk about two different kinds of intensities in the presentation so far, okay? The first intensity that I talked about was the fraction of peaks within a spectrum that matched, okay? And that is that goes into the confidence measurement for a peptide identification, but it doesn't say anything about the peptide abundance, okay? Where we get the peptide abundance is from the MS1 intensity, okay? And so they're two totally separate, I think for the most part, unrelated things. Does that help? I'm going to talk more about the spectrum intensity in a second. But with respect to quantification, we're just looking at MS1 intensity, and that does not really feed into whether a peptide is identified correctly or not. It doesn't really a factor there. We could be totally wrong about it. For instance, imagine that a peptide was not in the database that we're using. Okay, and as I said before, we're just simply for every spectrum we're going to give its best match, not the right match. Okay. So if the best match is a false positive thing and it's a super intense peptide, you can see how the MS1 intensity doesn't have anything to do with whether or not that assignment was done correctly. It's really only the MS2 fractional intensity that kind of where that shows up. And then that's only a bit of a partial factor. Is that helping at all? Maybe after I talk about like the other intensities like later, it'll crystallize better.
No, I got it. Yeah, thanks.
Yeah.
The other thing, maybe I don't know if it's relevant now. Maybe I'll mention it. So maybe you'll talk about it later. But in practice, I saw that there are various columns for the intensities, right? So you actually compute various intensities. So I spoke a little bit with Rachel about this. I mean, and she suggested I proposed to aggregate them all. What do you normally do with all those kind of intensity columns? Do you take the best? Do you aggregate? Do you sum them, or what?
I guess I don't totally understand the question, Simone. Like if you're talking about MS1 intensities or like MS2 intensities.
It's the flash LSQ output.
I'll show you later. Like I'll show you later where I got this from. I got this from the data we shared.
Okay. All right. So I'm going to go on then. I just wanted to give you guys a couple examples of spectra and like what a good spectrum looks like and what like kind of a weak spectrum looks like. So this spectrum was the highest scoring spectrum from that HeLa data set. Okay, I just picked the top one. Okay. And if you look along the top, there's a bunch of like blue L's here and a bunch of like purple L's. Okay. And basically what that means is that we were able to see fragment mass that corresponded to that. So this first blue L here is like 3 amino acids in, and that's a B3. So B1, B2, B3. So if you look down here, you see a B3 that's like marked, okay? Then we don't see anything B4, B5, B6 until B7. And so if you look down here, you sort of see B7. So one thing that we look for in a good identification, if we're like looking towards fragmentation, and Erin is like really the world expert on this call, so she can correct me if I'm just like off base
Please
here.
do not
like...
call me the world expert. Lots of colleagues who would beg to differ.
We like to see consecutive ions. Okay, that's like a positive thing. B and Y both. We most often see like more ions on the Y side when we use a trypsin digestion, because so most peptides are going to end with lysine or arginine. Lysine and arginine like pretty much are easy to ionize. They have a charge on them, and so it's like really easy to see these fragments on this side. This side is like the B side is the carboxy terminus, and so we're sort of like dealt a blow there right from the start because it's got that sort of like negative charge, and so it's like not unusual to see lower coverage on that end. But anyway, you can see that there's a few little gray peaks. I don't know how well it's showing up on your monitor, okay? But most of the big peaks in this spectrum are covered, okay? And so if you look at the score here, which is probably hard to see, it's 42.429. And what that score means in like MetaMorpheus world is that there's 42 matching fragment ions, and 42.9% of all the intensity in the spectrum is accounted for by matches to these ions. Okay, so this is you can see even with the very best match in that entire experiment that we don't have complete end-to-end sequence coverage, right? Particularly on the B side, there's like missing things. And so even with this one, there might possibly be some question as to whether we got it right or not. Okay. This is an example this is like the lowest scoring example from this particular file. Okay. It's still a pretty good identification. You know, it's not uncommon for this because we have like a little bit of a length problem with MetaMorpheus score, because like, since we just count fragment matches, short peptides are somewhat undervalued, you know, because they can, you know, like, you know, you can only have 2 times the sequence length total possible matches. But anyway, we have a very good Y-ion series here. This is like really quite excellent, okay? The fact that we only got 1 B-ion, like not unusual, but you can see the intensity of these like fragments is like severely diminished, and that there are a lot more gray peaks in here. In fact, if you look at the score, we have like basically only accounted for about 5% of the intensity of this spectrum for this match. And you can probably easily imagine like how many other spectra could match, like just sort of at random, to the variety of peaks that are here at like out of a level equivalent to what we got here. The fact that we think this is a good match is owing in part to the fact that we have so many consecutive ions in a row, and it's not like just totally scattershot. Okay, I wanted to give you some I mentioned ambiguity before, but I
asked a question on the last slide. Sorry.
Yeah.
So the this spectra would be for just one particular mass that would be match the mass of that peptide you show here.
That's right.
Correct. So all of those other peaks, it can't be the case that this is actually a much larger peptide that would give you all these additional peaks. So it must be, is the best explanation here that there are multiple peptides here with the same mass that are all in the same group?
Right. So one thing that I didn't get into so far, and I think it was just a case of a thing that I overlooked, an obvious thing that happens all the time, is that peaks, as I mentioned, like coming out of the column, multiple peptides are always coming out. Okay. And then we have that MS1 spectrum. And then the MS spectrometer selects peaks for isolation. And so the isolation window, like in bottom up, might be like 2 or 4 mass units. Okay. Within that, basically any peptide that's coming out, you know, with like charge 1 within 2 Daltons will be co-isolated. But since we're operating in like mass to charge space, what that means is like, so for instance, an 800 Dalton peptide charge 1 is going to show up at the same spot as a 1600 Dalton peptide charge 2, and a 2400 Dalton peptide charge 3, and a 3200 Dalton peptide charge 4. They're all going to be like stuck there in that window. Okay. Not only that, but the window sort of expands proportionally. So if it's 2 Daltons for 800, then it's like 4 Daltons for 1600, and it's like I don't know if I can do the math, like, you know, 12 Daltons for 2400, and so really it's often the case that there's lots of co-fragmentation occurring. So yes, Colin, in this particular example, there are other things that are being isolated and fragmented at the same time. One thing that MetaMorpheus does that I haven't talked about is that in the data file that's produced by the mass spectrometer, they will tell you we isolated 800 M/Z for this MS2 spectrum. Okay, and most search engines just sort of take that and go with it. What MetaMorpheus does is we go back to the MS1 spectrum and we look very closely to see if there are other peaks in that vicinity, and we attempt to match them all. Okay, and so in this particular example, I don't know if it happened or didn't happen, Colin, but if we looked at the MS1 for this particular peptide, which is it says the mass was 1228.5. It's possible that we found other peaks at that mass to charge in the MS1 spectrum, and we attempted to match them all, okay? So what we do is provide multiple identifications for a single isolation event, if it's possible. Does that help?
Yes, I think so. I think clarifying that it's the mass to charge ratio complicates things here, right?
Yeah, like quite a lot actually. It sort of surprises you when you see a peptide whose mass is completely different. You're like, wait a minute, and then you realize, yes, because we're in mass to charge space, that you can see very different mass peptides matching from the same isolation event.
Michael, just to build on that, when you said that you go back to the MS1 and you try to match multiple events that happened, do they then all get reported as long as they're all above the acceptable score?
That's right.
Okay.
So what we do is we duplicate the MS2 scan, and then we add the new parent. So if we went back to the MS1 and it said like, oh, it looks to us like there was 4 things isolated,
Yeah.
we would make 4 copies of that MS2 spectrum and use 4 different parent masses and then match all 4 of those. And then all 4 would be included in the results.
Nice. Okay. Thank you.
Yep.
So to clarify, so each spectrum can be used for multiple peptide matches.
Yes, absolutely. And so if you were to look at the output and then just look at the scan number, for instance, you could make a histogram by scan number, and then you could count, you could sort of sort it by scan number or whatever, and then you would easily see cases where, this was done, okay? Because the scan numbers will match.
Okay. So I thought reading some papers that they would take the best hit for each spectrum, but that sounds like that's not.
No, it's still, that is still true. Okay. So I'm just going to sort of slowly say this. Okay. So let's say that what we did, we had a case where we think that there was 4 things isolated. Okay. Then we make 4 copies of the MS2 spectrum, each with one of those 4 parent masses. Okay. And then we are going to select peptides from the Target and Decoy database that have those theoretical masses. And then we're going to report the best match for that combination of parent mass and MS2 spectrum. Okay. But the fact that the parent mass is going to be slightly different for all 4 of those things is we're going to be selecting different subsets of Target and Decoy peptides whose masses match that parent mass. Does that make sense, Colin? So we are always reporting the best match for a given theoretical mass and MS2 spectrum, but you can still have multiple matches for an isolation event because there can be multiple peptides isolated and fragmented.
Right. So it's the best match per spectrum mass pair.
Yes, that's correct. And it's only one. So it's either Target or Decoy, like not both. It's like winner take all in our software.
Great, thanks.
So to clarify this, when you say it's different masses, it's a case where maybe one peptide is 500 Daltons and a +1 charge. And then maybe another peptide is 1,000 Daltons with +2 charge.
That would be one example. It can also be the fact that, they can be just like a little bit different. It could be 500 +1 and 500.1 +1. Okay. You know what I mean? There can be very, very, very small mass differences, and that's like not uncommon at all. Okay. Just so long as they're within that isolation window. You can get a lot of peptides within a few Daltons.
Mm-hmm.
Okay, so here's some real examples of ambiguity that I found in that results list, and I just wanted to kind of share that with you. So what this means is that these peptides had exactly the same MetaMorpheus score to very high tolerance, okay? The first example on the top, you can see the isoleucine to leucine at the second to last amino acid. So here's an example, where both of those peptides were present in the proteome. And obviously, because isoleucine and leucine have exactly the same mass, we can't tell which it is. Okay. The second example I have here is one where there's Ptm ambiguity. So the base amino acid sequence is the same, and so here the vertical bar is like separating the two peptides. But in the first case, we have hydroxyl, which is OH on proline, which causes an additional 16 Daltons from the oxygen, because the oxygen kind of just sneaks in between the proline and a hydrogen. And then the second case is where we have oxidation of methionine. And again, that's 16 Daltons. So we know we've added 16 Daltons somewhere, but we didn't have any fragments that could distinguish these two things. And so it could, each thing is equally likely. Okay, they probably come from the same protein, so it wouldn't necessarily affect protein inference, but it is a complication. Okay, the next example is one where we have like amino acid transposition. So each of those peptides is composed of the same amino acids, but you can see the arrangement is all scrambled. Okay, and we did not have any distinguishing features which allowed us to distinguish which of those three things it against. And those things probably come from different proteins. So that's a complication. The last example is where we have like different amino acids. Again, the mass of this thing by some random chance ended up being the same mass, even though the amino acid composition is like substantially different. And the fragmentation couldn't distinguish the two. Okay. So these are, like I said, those are just examples that I had from this one experiment to illustrate the point. As far as FDR goes, as I mentioned before, FDR applies to the whole group. And so that means all peptides with that score or higher have whatever X% chance of being false positive. We don't know anything about any individual things. One thing is like we're missing certain spectra, like 1%, right? Because it's like winner take all, meaning we're not actually reporting the best target match for every spectrum, we're just reporting the best match. And so if we use a different decoy database, those winners and losers will change identity. This is like a really subtle thing, okay? But if you use only one decoy database, which is the reverse of the target database, and that's all you do, basically the winners and losers are determined by random chance. And so if you scrambled the decoy database again, the winners and losers could change, okay? And so there is some variation in the reported list. If there's any bias in the databases, then the equivalence fails. And we don't have any measurement of the individual assignments. So, so now I'm going to talk about.
Sorry, Michael. Yeah, here. So I thought the decoy was actually computed on the sample specific measurements that you have. So apparently it's it's kind of taken from whatever, like an available database that is always there, right?
No. What we commonly do is when you do a search, you have to provide a target database. Okay, we take that target database and reverse all the protein sequences left to right. Okay, so basically the order is reversed, and so and then we basically assume that like no peptide in this reverse database is shared with the target database. Okay, so it changes every time, and it's basically the same size as the target, but it doesn't come. There's no reference decoy databases that are used sort of separate and apart from the target, right? We create it on the fly from the provided database.
Okay, now I got it. So it's like the sequences can change, but then every time it's computing on the sample that you're.
Yeah, that's right. And the point I was just trying to make is like, and I'm going to get to it in the next slide actually. Okay, so this is a bit of a random paper, but like pretty much everything that comes from like Bill Noble is like, that's like sort of like gold standard ground truth. Anyway, this is just a little thing that talks about how we can get over the fact that the winners and losers can be just picked randomly. And the way to get around that is to use multiple decoy databases and then take the average, okay? So that, and that's basically reduces the variance you get from like multiple searches. It's not something that we do in our software. Obviously, the more databases you use, the more time it takes. But if you're really interested in a particular thing, this can be a way to get past that sort of like randomness of the single decoy database. All right, so now we're going to talk about individual confidence metrics. So this is for the single peptide. Like historically, one of the first ways where this was done was with something called the Q value. And the Q value is basically the same as the FDR, but FDR is like basically given at a specific value, whereas a Q value is like, it's basically the running FDR, okay? So if you go back to the PSM's experiment that I talked about, where everything is sorted from like high to low, if at every single PSM or peptide, you compute the ratio of decoys to targets up to that point, you will get a Q value for that peptide and all things above it, okay? And so here is a case where PSMs and peptides at the top will have a much lower Q value, and therefore the probability that there'll be false positives will be much lower. And then as you move down the list, that Q value will go up. And as it goes up, then the confidence about whether that, the probability of that being a false positive will also go up. So this is kind of the first and sort of easy, low-hanging fruit way of like finding out an individual confidence metric for an assignment, but it's still sort of a group-wise thing and not very happy, or not very satisfying. The next thing that sort of Gloria brought up before was the E value, okay? The E value basically gives you a way to compute the probability of a match by random chance. And so you don't even necessarily need a decoy database at all. What you do is you look at the count of fragments in the spectrum, and you look at the count of possible matches from your target, and then you pick that many you pick a bunch of massive values by random chance up to the length of your peptide, and then you compute the sort of distribution of probabilities, okay? So imagine a case where there's 200 masses in the fragmentation spectrum, and there's a 10 amino acid long peptide, okay? So if you have a 10 amino acid peptide, you can have 20 fragment matches. And so what you're going to do is you're going to pick 20 M/Zs at random from the spectrum, and then you're going to count how many of those M/Zs matched the 200 peaks that were there. Okay, so that's just going to be like a random chance kind of thing, and you might do that a bunch of times. All right, just in order to, and so basically, if you get, you find that the average random chance for this would be like 3 or 4, and you happen to get 9, then you call that match good. And if the match to your actual peptide is below that, then you basically call it bad. In practice, I find that this is not an effective strategy, but it does have its proponents. And the reason is that when you're picking peaks at random, the peak distribution doesn't really match that of a natural peptide. And I talked about that earlier, the importance of a decoy. The decoy really has to look like a target, like with respect to Mother Nature. Otherwise, it's not going to be a very good benchmark to match against. And so with the E value, just choosing M/Zs at random from all possible M/Zs, you're basically creating, lists of M/Zs which never would occur in nature. And so I feel like it's sort of like under-reporting the confidence. I mean, you're biased the wrong way. You're giving too much to the target match, and that's too little to the sort of quote unquote decoy. And then sort of the last and probably like the most prominent thing recently where you actually get an individual confidence measure is the posterior error probability. There's a program that many people use. It's called Percolator. It's a support vector machine that takes as input the PSMs that you get from your search, and it rescores and resorts all of the peptides based on additional criteria. We do something similar in MetaMorpheus, and so I'm going to describe that to you now. We use what's called a binary decision tree, and here it's still like a supervised training exercise. Basically, what we're doing is providing the results to the machine, and we're saying these certain results were true and these certain results are false. And then basically we're training on like a subset of the data and then applying it to like the remaining set, such that we never train and test on an overlapping set. And we sort of do this like multiple times. But and I'm going to show you the attributes in a second. But basically how a binary decision tree works is that like automatically tries to separate samples, in this case, into like true and false, target and decoy, based on criteria, individual criteria, whether it was like this or that. And so basically it's trying to produce pure groups of targets and decoys by applying a series of questions. And then at the bottom, the individual probability is based on the ratio of targets, the decoy, and the leaves. Okay, they all seem sort of like complicated, but I'm gonna show you like the kind of attributes and the questions you're asking. And here, Simone, is like where you see in the second block from the top, intensity is showing up. So we use total matching fragment count. That's like the MetaMorpheus score. We use like fractional intensity. And so here what you can kind of see is that on the y-axis, we've got the, it's basically the fraction of targets with that value. So if you look in the first graph here, the total matching fragment count, once we get up to 10 fragments, it's basically like, 100% of things with 10 fragments are targets, okay? And at the bottom, as you can imagine, it's going to be 50-50 because that's our criteria for like target decoy. All right. This intensity is the fraction of matched spectrum intensity, not the MS1 peak intensity. And so you can sort of see once you get up to this value of intensity, almost all things are targets. The reason it gets like weird here at the end is like simply because there's like a tiny number of like random examples with those things. This is not a histogram based on abundance. It's just simply based on the fraction of things appearing at a certain value. Delta score is quite interesting. That means like if you were to look at the best match for a spectrum and the second best match, when the scores between those gets higher, then we're more likely to be correct and so forth. So these are all of the things that we factor in. And once we do this, every single match in the entire list, all the PSMs and all the peptides are given a posterior error probability, which is the probability of being a false positive, okay? So then you can like resort those, and then if you're interested in a particular value, you can kind of look that up. That's about all I wanted to say there. Do you guys have any questions before we go on? I realize that's a bit more complicated, but I just wanted you to know that we do have individual assignment confidence metrics available. All right, now this is like one slide because we're really interested in protein inference, okay? And I just wanted to tell you how we're applying protein false discovery rate to the list of inferred proteins, okay? We use something called the picked method, all right? And in the picked method, the proteins are ranked from top to bottom based on a single peptide that's the highest scoring peptide for that protein, okay? It doesn't have anything to do with how many peptides went into like saying whether that protein exists or not. That's sort of like dictated by protein inference. But once the inference is done, we're picking the top peptide for each protein as the example and sorting things accordingly, okay? The reason we call this the picked method is because we pair the target protein with the decoy protein at the same accession. And whichever has the higher peptide score, we keep that one and throw the other one away. Okay, so this is a sort of a strange little beast, but basically if the decoy happened to have a higher scoring top peptide than the true one, we would throw the true one out. Okay, and so these things are all sorted from top to bottom. And again, we're using a 1% sort of cutoff. But people tend to like that, but this is really, I mean, this is soft earth as far as I'm concerned. You know, it's what we do. I think it's maybe the best thing we do, but it's a real sort of heuristic, you know. Yeah, I can stop sharing unless people have specific questions about any of the slides.
I have one slightly burning question, which is with this protein level FDR, my understanding is that all of the statistical methods are for protein identification, in quotes, like just identifying a protein from a gene, and
Yeah,
that there's
right.
nothing developed for protein isoform or proteoform level FDR.
So, yeah, so as far as isoform level things, I would apply it exactly the same way. Like in fact, it's like not unusual for me to use protein isoforms in the protein database. That's like common for me. And I treat it the same way. And I treat it to protein groups. Some people don't use protein groups at all in this like calculation. So the answer is like a qualified no to your question. I don't always group things by the gene. I just let them fall out of the inference algorithm, and you understand our inference algorithm based on previous discussions. And so like a proteoform thing is a totally different thing because we're not really doing protein grouping so much. We're really focusing more on proteoform identifications than proteoform group identifications. And so that's kind of a separate discussion.
Yeah, you know, I'm trying to figure out why I'm thinking this, but I see it as different when you go to the protein isoform level. So maybe that's a discussion, because I'd like to learn a little bit more about why you're so you're comfortable with applying these approaches at the isoform level. And I'm just I think with like having a lot of peptides that are shared and very few unique peptides, I just wonder, like, from like the statistical assumptions, if they hold or not. But yeah, I don't want to prolong the discussion, but maybe it's like an opportunity to talk more about this later, have like this as an agenda.
Right. I mean, just quickly, I can say is like when you include protein isoforms, like I said, and that's like not unusual for me in a regular proteomics experiment. You know, like you're actually giving opportunities for real sequences that exist in the sample to be matched. And those things can dictate a protein group, right? And so if you include protein isoforms and there happens to be a unique peptide to one of those isoforms, that can dictate it for the group. You know, it might not be the canonical isoform or the longest or whatever, but you know, you have the potential for like pure protein groups when you do that. Okay, like I just sort of feel like that allows for like more accuracy. You know, when you don't, as I mentioned early in the talk, if your database is incomplete or doesn't match your sample, then you know, like all you can get are false positives or decoys, right? We're going to report the best match for every spectrum. And if the spectrum doesn't have its correct match as a possibility, it's going to match something else, and that's going to get reported. So including protein isoforms in the search provides an opportunity to get a correct match for some things that you would otherwise like not be able to.